A 10 GB comma-separated values file takes 12 minutes to process in Pandas, consuming 40 GB of random access memory due to memory fragmentation. Polars processes the identical file in 14 seconds using only 12 GB of random access memory. This 50x speedup is achieved by shifting from eager execution to a columnar, memory-efficient architecture built on Apache Arrow and Rust. Pandas uses NumPy arrays, which are row-oriented and struggle with memory allocation overhead on large data frames. Polars leverages memory mapping and zero-copy reads, eliminating the need to load the entire dataset into contiguous memory up front. This fundamental architectural difference is the key to solving system bottlenecks in data pipelines exceeding 5 GB. We immediately transition to the syntax required for this critical shift. Pandas operates eagerly. Every operation executes immediately, creating intermediate copies of the data frame. This memory duplication is the primary cause of out-of-memory errors in production systems. Polars defaults to lazy execution when using the scan CSV or scan parquet methods. Lazy execution builds a directed acyclic graph, or DAG, of operations. The query optimizer analyzes this DAG before any computation starts, performing predicate pushdown and projection pushdown. Predicate pushdown means filtering happens at the source, minimizing data read from disk. Projection pushdown ensures only necessary columns are loaded. This optimization step is crucial for the massive performance gains, especially when dealing with complex multi-step transformations. Understanding the DAG is essential for debugging performance issues in Polars pipelines.
Refactoring Pandas read.csv to Polars scan CSV is the first mandatory step. Instead of pd.readcsv.data.csv, we use pl.scancsv.data.csv. The scan function returns a lazy frame, not an immediate data frame. This lazy frame is the foundation of the directed acyclic graph. When reading Parquet, Pandas requires specifying engine parameters, often defaulting to PyArrow or FastParquet. Polars natively uses Arrow, simplifying the call to pl.scanparquet.data.parquet. Crucially, Polars infers the schema during the scan, but does not load the data. For system analysts, defining the schema explicitly using with columns and cast immediately after the scan prevents unexpected type coercion issues, which are common performance killers in Pandas when dealing with mixed type columns. Explicit schema definition ensures memory efficiency from the start. Pandas uses bracket notation and the .loc or .iloc accessors for selection and filtering. Polars uses the .select and .filter methods exclusively. To select columns A and B, Pandas uses df.a.b. Polars uses df.selectAB or df.selectpl.calla, pl.callb. For filtering, the Pandas expression df.df.c greater than 10 translates directly to Polars df.filter pl.callc greater than 10. Notice the mandatory use of pl.call. This function creates an expression object, which is the core unit of computation in Polars' lazy engine. Expressions are chained together within the select, filter, or with columns methods. Avoid using standard Python list comprehensions inside Polars methods, as this forces eager evaluation and defeats the purpose of the query optimizer.
Grouping syntax requires careful translation. Pandas uses df.groupby key.ag value sum mean. Polars uses the groupby method followed by ag. The Polars equivalent is df.groupby key.ag pl.call value.sum.alias total sum pl.call value.mean.alias average mean. The key difference is the explicit use of the .alias method to rename the resulting aggregated columns. This prevents automatic, often verbose, column naming generated by Pandas. For multiple aggregations on the same column, define the expression once and reuse it, or list them within the ag array. When calculating rolling windows or exponential moving averages, Polars provides optimized window functions that execute significantly faster than their Pandas counterparts, especially on sorted data. The entire chain of lazy operations, from scan CSV through filter and group by, only defines the computation plan. No data processing occurs until the .collect method is explicitly called. This is the execution trigger. If you omit .collect, you are only manipulating the directed acyclic graph, not the actual data. System analysts must place .collect strategically. For instance, if the pipeline involves writing the result to a database, the .collect should precede the database write operation. Conversely, if the pipeline involves multiple intermediate steps that are memory-intensive, avoid premature collection. The query optimizer works best when it sees the entire chain of operations before collection. Monitoring memory usage before and after the .collect call provides immediate feedback on the
Pandas often fails when the dataset size approaches or exceeds available physical random access memory, leading to swapping and eventual memory errors. Polars mitigates this through memory mapping and chunking. When using scan CSV, Polars reads data in chunks, processing them sequentially without loading the entire file into memory simultaneously. This allows processing datasets significantly larger than physical random access memory. For extremely large files, ensure the system configuration allows sufficient file descriptor limits. If a transformation requires sorting a massive column, Polars might still require temporary disk space. System configuration should allocate fast solid-state drive space for temporary files, which Polars uses efficiently during complex sorts or joins, preventing system crashes that characterize Pandas memory exhaustion. Existing systems often rely on Pandas data frames for visualization libraries or legacy functions. Converting between the two formats is necessary for integration. Use df_polars.toPandas to convert a Polars data frame back to a Pandas data frame. This operation is eager and copies the data, so it must be the final step in the Polars pipeline, minimizing the time spent in the less efficient Pandas environment. Conversely, converting a Pandas data frame to Polars uses pl.fromPandas df_pandas. This conversion is fast because Polars can often leverage the underlying Arrow memory structures if the Pandas data frame was created using PyArrow backends. However, be mindful of potential type mismatches during conversion, especially with complex nested data structures like lists or dictionaries. Before deploying Polars, verify the environment configuration. Ensure the latest stable Polars version is installed, as performance improvements are frequent. Set the number of threads Polars uses via the Polars max threads environment variable. Typically, setting this to the number of physical cores optimizes parallel execution. When running on cloud infrastructure, select instance types optimized for high input-output operations per second, as Polars heavily relies on fast disk access during scanning. Always profile the lazy execution plan using df.explain before collection. This visualizes the directed acyclic graph and confirms that predicate and projection pushdowns are correctly applied by the optimizer, validating the refactoring effort and ensuring the 50x speedup is realized in production.